Namaste students, back to the class. Hope you are enjoying your days. Now children, we are already done with classification of haloalkanes, the nomenclature of haloalkanes, and some of the examples which we discussed were really challenging. With this, now we move to methods of preparations of haloalkanes. So, look at the board. See, in the methods of preparations of haloalkanes, we have got 5 methods. We can prepare haloalkanes from alkane, from alkene, from alcohol, by halide exchange method, and finally the Hunt-Sticko reaction. So there are in all 5 methods to prepare haloalkanes. The first method is from alkanes. In order to prepare a haloalkane from alkane, we make use of halogenation, wherein the hydrogen atoms of alkane are replaced by halogen atom. We replace one hydrogen atom of alkane by one halogen atom in order to get a haloalkane, that is a monohalogen derivative of alkane. This halogenation of alkanes is further classified in the 3 categories. We have got 3 subways, and they are chlorination, bromination, and iodination. During chlorination, we treat alkane with chlorine in presence of ultraviolet rays or diffuse sunlight. Like here, if you look at the board, we are treating ethane molecule with chlorine in presence of ultraviolet rays. As a result, we are getting ethyl chloride. The ultraviolet rays are absorbed by chlorine molecule, which makes the chlorine molecule energized. The molecule becomes excited and it becomes highly unstable, so it undergoes homolytic fission to produce chloride-free radicals. These radicals attack the molecule of alkane to give the corresponding alkyl halide. Since this reaction is carried out with UV rays as the catalyst, we call it a photochemical reaction because the photons in the UV rays initiate the reaction. This reaction cannot stop at monohalogen state, but it continues till all the hydrogen atoms of alkane are replaced by halogen atoms. So we also call it a chain reaction. Since homolytic fission of chlorine produces free radicals, we call it free radical mechanism. Now, in order to get monohaloalkane as the major product and not all kinds of halogen derivatives, but to get a monohaloalkane as the major product, the reaction is carried out with excess chlorine. The reaction is carried out with excess chlorine. When we look at the next example, propane reacts with chlorine in presence of UV rays. Unlike this reaction, we get 2 products. Because the chlorine molecule can not only attack the primary carbon of propane, but it can also attack the secondary carbon of propane. As a result, we are getting 2 products, 1 chloropropane and a 2 chloropropane. Now, in the order of reactivity of hydrogen atoms, a tertiary hydrogen atom which is on a tertiary carbon is more reactive than secondary, and the secondary is more reactive than primary. So obviously over here we are getting secondary alkyl halide, that is 2 chloropropane as a major product with 55% and 1 chloropropane with only 45%, which is a minor product. With this, now we move to the next halogenation, which is bromination. Bromination is an electrophilic substitution reaction. Bromination needs the catalyst aluminium bromide, which is an electrophile, and it is a Lewis acid. This electrophile attacks bromine to generate another electrophile, bromonium, which replaces the hydrogen atom by bromine atom. So ethane reacts with bromine with Lewis acid aluminium bromide to give ethyl bromide, and the byproduct is HBr. The reaction needs little warm conditions. Aluminium bromide behaves as the catalyst. And the last type of halogenation is iodination. Now children, direct iodination is not possible because, say if I take a molecule of ethane and I treat it with iodine, I'll be getting ethyl iodide and hydroiodic acid. But we have learned hydroiodic acid is a very strong reducing agent. This reducing agent will attack back the ethyl iodide to give back alkane, and hence iodination will become reversible. In order to avoid the reversibility of iodination, we are making use of strong oxidizing agents which are not catalyst, because catalyst does not take part in reaction, but they take part in reaction. So they are agents of the reaction. So the reactants in iodination will be a alkane, iodine, and any one of the reagent, that is the oxidizing agent. And here we can see the examples. Ethane reacts with iodine in presence of oxidizing agent mercuric oxide to give ethyl iodide. Now with ethyl iodide, the HI which must be produced, with ethyl iodide, the HI which must be produced will be attacked by mercuric oxide to give mercuric iodide and a molecule of water. So this is nowhere now, because its effect has been totally nullified by oxidizing agent. We can balance the reaction, children. 2, is one molecule we need. 2, this will be 1, 1. Then we go to the next example, where methane is treated with iodine in presence of iodic acid as the oxidizing agent to give methyl iodide and water molecule. We just balance the reaction. 5, 2, 1, and this will be 5, 3. Similarly, another example, ethane reacts with iodine in presence of nitric acid to give ethyl iodide, water, and ammonia. Now in this reaction also we can balance these 8 molecules we need over here and 4 iodine over here, and this one is sufficient, this 8 molecules over here, and 3 molecules of water, because 3 to 6 hydrogen, 6 to 9 over here, and here we have got, it's 48, so 40 over here, so balanced. So this completes the first method, that is halogenation of alkanes. Now we have not done fluorination, because the reaction of alkane with fluorine is very, very violent and uncontrollable. The reason in very good detail I have given in my notes. Just read it. One reading is sufficient over here. I think the lecture is clear to everyone. Keep studying. Padhai karte raho. Stay blessed. Love and blessing.